Links and joints. Links and joints. Joints. Links. Two DOFs. End effector. Robot basis. DeNavitt, Hartenberg details and examples. Chapter 2 Robot Kinematics, Position Analysis. DeNavitt Hartenberg representation. Symbol terminologies. Chapter 2 Robot Kinematics, Position Analysis. Rotation about the z-axis. D. The distance on the z-axis. A. The length of each common normal, joint offset. The angle between two successive z-axes, joint twist. Only N and D are joint variables. Z-axis aligned with joint. Joints U. Links S. X-axis aligned with outgoing limb. Y-axis is orthogonal. Joints are numbered to represent hierarchy. UI1 is parent of UI. Parameter I1 is outgoing limb length of joint UI1. Joint angle, Chi, is rotation of 11:1 about Z1 relative to 11. Link twist, I1, is the rotation of its Z-axis about 11:1 axis relative to Z-axis of I first frame. Link offset, D1, specifies the distance along the Z1 axis, rotated by I1, of the ith frame from the I first x-axis to the ith x-axis. DeNavitt Hartenberg representation procedures. Start point. Assign joint number n to the first shown joint. Assign a local reference frame for each and every joint before or after these joints. Y-axis is not used in DH representation. DeNavitt Hartenberg representation. Procedures for assigning a local reference frame to each joint. All joints are represented by a z-axis. Right-hand rule for rotational joint, linear movement for prismatic joint. The common normal is one line mutually perpendicular to any two skew lines. Parallel z-axis joints make an infinite number of common normal. Intersecting z-axes of two successive joints make no common normal between them. Length is 0. Chapter 2 Robot Kinematics, Position Analysis. DeNavitt Hartenberg representation. The necessary motions to transform from one reference frame to the next. Chapter 2 Robot Kinematics, Position Analysis. I. Rotate about the Zn axis an angle of n+1. Coplanar. 2. Translate along Zn axis a distance of dn+1 to make xn and xn+1 collinear. 3. Translate along the xn axis a distance of n+1 to bring the origins of xn+1 together. 4. Rotate Zn axis about xn+1 axis an angle of n+1 to align Zn axis with Zn+1 axis. DeNavitt, Hartenberg parameters dash. A general explanation. DeNavitt Hartenberg notation. Only N and D are joint variables. Zi, 1. Yi-1. Yi. Zi. Xi. Ai. 1. Di. Xi-1. I. 1. Idea. Each joint is assigned a coordinate frame. Using the DeNavitt Hartenberg notation, you need 4 parameters to describe how frame I relates to a previous frame I-1. The parameters / variables, A, D. Rotation about the z-axis. D. The distance on the z-axis. A. The length of each common normal, joint offset. The angle between two successive z-axes, joint twist. The AI1 parameter 1, AI1. You can align the two axes just using the 4 parameters. Zi, 1. yi minus 1, yi, zi, xi, ai, 1, di, xi minus 1, I, 1, 1, ai1. Technical definition: ai1 is the length of the perpendicular between the joint axes. The joint axes are the axes around which revolution takes place, which are the zi1 and zi axes. These two axes can be viewed as lines in space. The common perpendicular is the shortest line between the two axis lines and is perpendicular to both axis lines. The alpha ai1 parameter. ai1 cont. Visual approach. A way to visualize the link parameter ai1 is to imagine an expanding cylinder whose axis is the zi1 axis. When the cylinder just touches the joint axis, the radius of the cylinder is equal to ai1. Manipulator kinematics. zi 1, xi minus 1, yi minus 1, I 1, ai 1, zi, yi, xi, ai, di, I, rotation about the z-axis. D, the distance on the z-axis. A, the length of each common normal, joint offset. The angle between two successive z-axes, joint twist. It's usually on the diagram approach. If the diagram already specifies the various coordinate frames, then the common perpendicular is usually the xi1 axis. So ai1 is just the displacement along the xi1 to move from the I1 frame to the I frame. If the link is prismatic, then ai1 is a variable, not a parameter. zi 1, xi minus 1, yi minus 1, I 1, ai 1, zi, yi, xi, ai, di, I, rotation about the z-axis. D, the distance on the z-axis. A, the length of each common normal, joint offset. The angle between two successive z-axes, joint twist. The I1, parameter 2I1, technical definition. Amount of rotation around the common perpendicular so that the joint axes are parallel. I.e., how much you have to rotate around the xi1 axis so that the zi1 is pointing in the same direction as the z-axis. Positive rotation follows the right-hand rule. The I1, parameter. zi 1, xi minus 1, yi minus 1, I 1, ai 1, zi, yi, xi, ai, di, I. 3. di1. The di1 parameter. The I parameter technical definition. The displacement along the z-axis needed to align the ai1 common perpendicular to the I common perpendicular. In other words, displacement along the z to align the xi1 and z axes. 4. I. Amount of rotation around the z-axis needed to align the xi1 axis with the z-axis. The di1 parameter. The I parameter. zi 1, xi minus 1, yi minus 1, I 1, ai 1, zi, yi, xi, ai, di, I. The same table as last slide. The Dinavit-Hartenberg matrix. Just like the homogeneous matrix, the Dinavit-Hartenberg matrix is a transformation matrix from one coordinate frame to the next. Using a series of DH matrix multiplications and the DH parameter table, the final result is a transformation matrix from some frame to your initial frame. zi 1, xi minus 1, yi minus 1, I 1, ai 1, zi, yi, xi, ai, di, I. Put the transformation here. Rotation about the z-axis. D. The distance on the z-axis. A. The length of each common normal, joint offset. The angle between two successive z-axes, joint twist. Example, calculating the final DH matrix with the DH parameter table. Dinavitt-Hartenberg link parameter table. The DH parameter table. Example with 3 revolute joints. Z0, X0, Y0, Z1, X2, Y1, Z2, X1, Y2, D2, A0, A1. Dinavitt-Hartenberg link parameter table. Notice that the table has 2 uses. 1. To describe the robot with its variables and parameters. 2. To describe some state of the robot by having a numerical values for the variables. We calculate with respect to previous. Dinavitt-Hartenberg link parameter table. Example with 3 revolute joints. Z0, X0, Y0, Z1, X2, Y1, Z2, X1, Y2, D2, A0, A1. Dinavitt-Hartenberg link parameter table. Notice that the table has 2 uses. 1. To describe the robot with its variables and parameters. 2. To describe some state of the robot by having a numerical values for the variables. The same table as last slide. D2 A0 A1. Note, T is the DH matrix with I1 equals 0 and I equals 1. Z0, X0, Y0, Z1, X2, Y1, Z2, X1, Y2, D2, A0, A1. The same table as last slide. Note, T is the DH matrix with I1 equals 0 and I equals 1. World coordinates. Tool coordinates. These matrices T are calculated in next slide. This is just a rotation around the Z0 axis. The same table as last slide. This is just a rotation around the Z0 axis. This is a translation by A1 and then D2 followed by a rotation around the X2 and Z2 axis. This is a translation by A0 followed by a rotation around the Z1 axis. Conclusions. World coordinates. Tool coordinates. Forward. Kinematics. Forward kinematics problem. The situation. You have a robotic arm that starts out aligned with the XO-axis. You tell the first link to move by 1 and the second link to move by 2. The quest. What is the position of the end of the robotic arm? Solution. 1. Geometric approach. This might be the easiest solution for the simple situation. However, notice that the angles are measured relative to the direction of the previous link. The first link is the exception. The angle is measured relative to its initial position. For robots with more links and whose arm extends into 3 dimensions, the geometry gets much more tedious. 2. Algebraic approach. Involves coordinate transformations. Example problem with H matrices. You have a 3-link arm that starts out aligned in the x-axis. Each link has lengths L1, L2, L3, respectively. You tell the first one to move by 1, and so on as the diagram suggests. Find the homogeneous matrix to get the position of the yellow dot in the X0, Y0 frame. Y3, 3, L2, L3, Y2, X3, 2, X2. H equals RC1. Texas 1L1RZ2, Texas 2L2RZ3. Rotating by 1 will put you in the X1Y1 frame. Translate in along the X1 axis by L1. Rotating by 2 will put you in the X2Y2 frame. And so on until you are in the X3Y3 frame. The position of the yellow dot relative to the X3Y3 frame is L3, 0. Multiplying h by that position vector will give you the coordinates of the yellow point relative the X0, Y0 frame. Y0, L1, X1, 1, Y1, X0. Slight variation on the last solution. Make the yellow dot the origin of a new coordinate X4, Y4 frame. Y3, Y4, 3, 2, 3, Y2, X3, 2, X2. Added. X4. H equals RC1, Texas 1L1 RZ2, Texas 2L2 RZ3, Texas 3L3. This takes you from the X0, Y0 frame to the X4, Y4 frame. The position of the yellow dot relative to the X4, Y4 frame is 0, 0. Y0, 1, X1, 1, Y1, X0. The inverse kinematic solution of a robot. The inverse kinematic solution of robot. Determine the value of each joint to place the arm at a desired position and orientation. RHS. Multiply both sides by A1 minus 1. The inverse kinematic solution of robot. The inverse kinematic solution of robot. We calculate all angles from x, pi, A1, A2, ni, oi, etc. Inverse kinematic program, a predictable path on a straight line. A robot has a predictable path on a straight line, or an unpredictable path on a straight line. A predictable path is necessary to recalculate joint variables between 50 to 200 times a second. To make the robot follow a straight line, it is necessary to break the line into many small sections. All unnecessary computations should be eliminated. Figure 2.30 Small sections of movement for straight line motions. Problems with TH. Degeneracy and dexterity. Degeneracy, the robot loses a degree of freedom and thus cannot perform as desired. When the robot's joints reach their physical limits, and as a result, cannot move any further. In the middle point of its workspace, if the z-axis of two similar joints becomes collinear. Dexterity, the volume of points where one can position the robot as desired, but not orientate it. Figure 2.31 An example of a robot in a degenerate position.